Welcome to Math 31. This is Lesson 3, the indefinite integral. So we're going to be looking at not a whole lot new mathematically, but some different notation and the way we're going to view anti-differentiation problems from here on in. The first big term is the process of anti-differentiation is called indefinite integration. So instead of being asked to to anti-differentiate or to find the antiderivative, we'll now say evaluate the following integrals or integrate the following. And as it states right here. So you see both. You see finding, evaluating. And I'm using the word indefinite right now. Later on we'll look at definite integrals that have a related but a specific meaning. And the integral symbol itself is this. You're going to see this all over the place, and from here on in your calculus career, it's sort of a slanted S, which is to represent sum, and the meaning behind that becomes clear in a short time as well. And the way it works, the symbols go like this. You'll see the integral symbol, and you'll see the function that you are going to integrate, and you're going to see this dx symbol. Now that's part of the integral itself. Must be there. It's very important. And it is also telling you that you are to integrate whatever the polynomial big f at x is. And then the result, the antiderivative, is f at x plus c, just like we were doing previously. So it's really just a notation thing. Now this is true, this statement I've given you is true, if and only if the derivative of little f is equal to big F. So the same sort of thing that we were dealing with before with just straight antiderivatives. So let's launch right into a few. Evaluate the following indefinite integrals. So number one. So nothing really changes except that getting used to the integral symbol itself and then the dx. And this is just going to be x, we add on 1 to the exponent, so we get x to the 3, and then that becomes our denominator, so we get 1 over 3 x to the 3, then plus c. So you still have to put the plus c for constant. Try another one. So here we get a slightly more complicated looking expression, but it isn't that much different. To work this one out, we first off express it in a slightly more convenient form. 8t to the 3 minus 5 plus t to the negative 2. Note, of course, that it's dt. And this would give us t to the 4. You could do this more quickly than I am, but then 8 over 4 minus, well, the 5 is there, t to the 1, and then t, add 1 on, and you get t to the negative 1, and then that becomes 1 over negative 1, and then plus c. So that's looking pretty routine. Cleaning it up will give us 2 t to the 4, then minus 5t, and then minus t to the negative 1. Plus c. Okay, so nothing really new, just the notation. Now, before we go any further, I'm going to show some of the properties associated with integrals that may come in handy. They're fairly intuitive. Most of you would, in fact, we've already done one already, so they will make sense, but they do give us a few more choices in how we want to tackle problems. So the properties go like this. If you have a constant, like a coefficient in front of the polynomial, you can take it right outside the integral symbol. Now that's really what we've been doing, because when we get the antiderivative, if we have a constant there, if we have a coefficient, we just ignore it, it's a passenger, and then multiply it into whatever denominator we get. This one could be useful. I've got it all written together here, but if you've got two polynomials being added together, such as the one number 2 that we just did, you can break it down into two separate ones if you want. Now there's a time when this is actually a good idea. Normally people don't worry about it too much. They just keep on doing it when the same way they've always done it, but it is a choice. So let's do a few more now that we have these tools in front of us. And just to keep us sharp, I'm going to use these properties. This one is a three-term, it's not really a polynomial, but an algebraic expression. And we could write this, if we chose, separate them, break them up. And this is optional. Most of you are going to say I'm not going to bother with it. But 2x squared. Well, we can write this as x squared, the integral of x squared with a 2 in front of it. Thing of it is, we have to make sure we keep the dx for that. Every integral symbol must have a dx. And then minus 5 multiplied by the integral x dx. So then the 2 can come out according to that property, and then we get x to the negative 3 dx. So I'm probably not selling the advantages of these properties very much. It seems to be a little more work. But in any case, we'll get x to the 3, and then 2 over x to the 3. And then this becomes x to the, it's x to the 1 now, so x squared, and then 5 stays, so 5 over 2. And then this one becomes x to the negative, add 1 on, you get negative 2, so we get minus 2 over that minus 2, and then plus c. So this one will finally break down to 2/3 x to the 3 minus 5 halves x squared, and then plus x to the negative 2. And then plus c. So nothing too complicated. But where things are going to get interesting is ones like this, because we're quite limited in what we can do with anti-differentiation, or we have been quite limited. We've been able to do single terms, as many as there are, for algebraic or polynomial or rational things, but we can't really deal with bracketed expressions like this too well, because really this may involve the chain rule or the reverse of the chain rule. So what we need to do is, as much as possible or where possible, is simplify first. So when I see something like this, I'm going to take this root x plus 1 and I'm going to FOIL it out. Now I'm going to do it off to the side. That's a choice of mine, and then I'm going to bring it back in. You can certainly keep it going in the 1. And you could also write this as x to the 1/2, which eventually we're going to have to deal with, but I'll keep it as a radical first off. FOIL it together because the whole thing's being squared, and so we get root x times root x is x plus root x plus root x. So those of you who are familiar with shortcuts for squaring binomials will know that you can just take the oi part and add it together in one step. So this becomes x plus 2 root x plus 1. So for us, this would become x plus 2 x to the 1/2 plus 1 dx. Now this one will work better for us, and we can break it up like I did previously or not, and I'm not going to bother. So this x to the 1, when we integrate this, we get x to the 2, and then that becomes the denominator. And then this becomes x. Be careful with this one. This is x to the 3 over 2. We add 1 on. So the term in front is, the 2 is there, and we multiply by the reciprocal of 3/2 because we're dividing by 3/2 on the denominator, so times 2/3. And then we add, this becomes just plain x. And then plus c. And then when we finish it off, we'll get 1 over 2 x squared plus 4 over 3 x to the 3/2 plus x plus c. And with these, you can either write it as I have it down there, or as I did earlier, just have it equal to that expression at the top. Very common. I would accept either, though. Let's try a few more related to all this. This one, probably one you'd want to do on your own and then just check the answer. Nothing really strange happening with this one. Again, make sure that you you FOIL it out first, and then go back to integrate. So 5x squared minus 3 to the 2. do this one quickly, it's the first term squared, so that's 25x to the 4. And then the second term would be minus 2 times AB. So that would be minus 2 times 15 is minus 30x squared. So it would be minus 15x squared minus 15x squared plus 9. So this expression would really be equal to this. 25x to the 4 minus 30x to the 2 plus 9 dx. So when we finish it off, or when we integrate it, we'll get x to the 5, and then 25 over 5 is 5. And then this becomes x to the 3. That becomes our denominator. So 30 divided by 3 is 10. And then this becomes plus, well, there's no x there. Remember, that is actually 9x to the 0. But really all you do then is just go x to the 1. So plus 9x, and then plus c. So not much ground broken with that one. Number 4 is interesting because of the nature of the polynomial, or the rational term, the 3x to the 4 or the denominator. Now, you can do this a couple ways. Some of you will be tempted, and quite correctly, to write that as x to the negative 4 and then expand it like that. That certainly works well. You can also FOIL it out the way it is. I'm going to write it like this. 1 over 3 x to the negative 4 minus 6x to the 4, and then multiply this out again. So I'm making sure I don't make a mistake with this, because if you make a mistake with a question like this, it'll happen in this stage as likely as not. So you really want to be careful, even though it's a simple foiling job. So 1/3 x to the negative 4 squared is going to be 1 over 9 x to the negative 8. And then the two middle terms, you're going to get 1/3 x to the negative 4 minus 6, or times minus 6x to the 4. 1/3 times 6 is 2, so minus 2. The x's go away, and then the next term will be minus 2 as well, and then plus 36x to the 8. So when we express this one in a simpler form, we get 1 over 9 x to the negative 8 minus 4 plus 36x to the 8 dx. And then, when we integrate it, be very careful, we'll get x to the add 1 would be negative 7. And I'm going to do this directly. 1 over 9 times 1 over 7 is going to be 1 over 63. I should say times negative 7. So I did that in one step. Be very careful. Do not make a mistake with it. And then you get minus 4x for the next term. The next term after that would be x to the 9, and then 36 divided by 9 is plus 4x to the 9, and then plus c. And then we're done. Now this one is actually, I lost an exponent on this. No, I'm sorry, that's okay. This one is as it should be. It's the next one that I dropped the exponent. Pause me and go through it yourself. There's nothing really difficult about this one, except that this would be 2x to the negative 1/3 plus x to the 1/2. Make sure you get a bracket around it. If you're not going to break it up, you do want to put a bracket around it so it's clear to any observer that the dx belongs to the whole thing. That is, you're trying to integrate the entire expression. So nothing that you haven't seen before. Add on 1. And so negative 1/3 plus 3 over 3 is 2 over 3. Now be careful, because this now becomes 2 times the reciprocal of 2/3, which is 3/2. So I'm taking care with it. I'm not making sure I don't screw up the fraction. Add on 1, and you'll get 3 over 2. And then 1 divided by 3 over 2 is 2 over 3 plus c. So this becomes 3x to the 2/3 plus 2/3 x to the 3/2 plus c. And this is the one that I wanted to have a 2 on for the exponent. Once again, pause me, have a look at it, and do it yourself if you like. Here as well, I'm going to write this as x to the negative 2, and then plus 1 over 2, and then that becomes x to the negative 1 over 2. And then that gets multiplied by x to the negative 2 plus 1 over 2 x to the negative 1 over 2. And FOIL it out whichever method you want. And you'll get x to the negative 4 for the first term. You'll get plus 1 half. And then make sure you carefully add those exponents. Negative 2 plus negative 1 half is going to be x to the negative 5 over 2. So 2 and a half. And then the middle term, the next middle term is going to be the same, plus 1 over 2 x to the negative 5 over 2. The last term is plus 1 quarter, and then negative 1 half plus negative 1 half is negative 2 halves, negative 1. So this is the integral of x to the negative 4 plus 1 half plus 1 half is 1, x to the negative 5 over 2, and then plus 1 quarter x to the negative 1 dx. So we integrate by adding, using the regular rules, add on 1 to the exponent is negative 3, and then this is negative 1 over 3. Then the next one is add on 1, so that's negative 3 over 2. So our coefficient would be negative 2/3, 1 divided by 3 halves. And then the last term, add on 1, and we're going to get x to the 0. And this is where things get interesting. We get 1 over 4 divided by 0. And here, we can't do it. So, in fact, we cannot integrate x to the negative 1. And I'll just put a yet. Now, in this course, we're not likely to have time to do the exponents and logarithms. There is a way to deal with that. But that's something that you do run into occasionally, because when you do take x to the negative 1, this is just sort of an observation on it. You add on 1 and you get x to the 0, but 1 over 0 is no can do. So that's something to be aware of, and I chose this example to illustrate that, but it's going to show up down the road. Now, number 7, so just to finish that one off, that's it. That's all that we can do with it for now. So I'm just going to leave it like that, and then when you do cover logarithms in, you work out a method to handle it pretty nicely. Pretty simple, actually. Now, sine x dx, nothing new with this one. You've seen the trig ones, but be really careful because the integral, or the antiderivative of sine x is negative cos x, and then plus c. So you need to remember that. Now, those are not on your formula sheet, so you've got to be very careful. You've got the regular derivatives. You just got to think backwards. And easy to check, because then the derivative of negative cos would be positive sine x. And then that's it. And then number 8, a little bit more complicated, but you've got to remember that the 3 remains as a passenger, and then the antiderivative of cos of 2/3 x is sine of 2/3 x, and then we multiply by 1 over k, that is 1 over 2/3. 1 over 2/3 is 3 halves. And so this will give us 9 over 2 sine of 2 over 3x plus c. And this one warrants a check. So let's differentiate the answer. So to differentiate 9 halves sine 2/3 x would be 9 over 2 times the cosine of 2 over 3x times the derivative of the inner, which is 2/3. Multiply all that out, and you will get, well, 18 over 6 is 3 cos 2/3 x. So we did it. Remember, if you have any doubt about your expression, check it by foiling or by differentiating. Thing is to remember is that for questions like number 6 or any of these bracketed ones, it's a little bit more complicated because in order to check your answer, you'd have to expand and do a little more work on the original. It's not going to take you right back to what you started with because it's in a bracketed factored form. So that's it for these questions. We're going to go on and develop some better methods for solving these more complicated ones, take a look at a few other sort of topics that relate to it, and then finally sew the whole thing together. Thank you for your time.